So today's lecture is about pumping lemma for context-free languages. What is pumping lemma? Basically, pumping lemma is a procedure which help us to pump those strings which we need to check for any of the given context-free language. So with the help of this pumping lemma approach, we can prove whether the language is context free or not. So technically it is a proof of contradiction, so we always use to prove that the language is not context free. So for any context free language which is generated by context free grammar contains these four tuples. The very first one is V, or the set of variables, sigma, set of terminals, S is the start symbol, and P shall be the set of productions. So what is the rule of a pumping lemma? The rule states that if A is a context free language, then A has a pumping length P such that any string S where S, the magnitude of S or the length of S is greater than equal to the pumping length may be divided into 5 units or pieces, such as S is equal to U, V, X, Y, Z. These 5 pieces must contain the following conditions. So what are the conditions? The conditions are in a way that these 5 pieces contains 2 iterative units which can come process again and again. So it is a loop fashion. So U is constant, V contains I, which help us in order to pump the string. There is another element X, then we are having Y, which contains the power of I, which also help us to pump the string. And finally the last element is Z, and this structure is should be in A for every I is greater than equal to 0. Second thing, the magnitude or the length of Vy must be greater than 0. The third condition is Vxy should be less than equal to the pumping length which we use to check whether the language is context free or not. So these are the 3 conditions which we need to satisfy in order to prove whether the language is context free or not. So as we have mentioned early in the beginning that it's a proof of contradiction, so we always assume that the given language is a context free language. Second, there is another assumption that it must have a pumping length P. So the string which can be produced with the help of context free language must contain a pumping length. It should not be of fixed length. Number third, all strings greater than P can be pumped. So if we are having a bigger string which is greater than the given pumping length, must be pumped or must be satisfied with the help of the given context free grammar. We need to find a string S in A such that S, length of S must be greater than equal to P. Then we need to split S into 5 parts, U, V, X, Y, Z, where U, V, I, X, Y, I, Z should not belongs to A for some particular I's. So if we are changing different I combinations or having different I selections, so there must be some words which are not the member of the actual context free grammar. If this happens, then we can say that the given language is not context free. The last thing, we need to show that none of these can satisfy all the 3 pumping conditions at the same time. So if any language after being pumped can satisfy all the three conditions, these three conditions, then we can say it is the language is context free. Otherwise we can say the language is not context free. So here's the example that we need to check. So here's the length, here's the language which produces a to the power n, b to the power n, and c to the power n strings such that n is greater than equal to 0, and we want to prove that this is not context free. So first we need to assume that the given language is context free, and with this assumption we can introduce a pumping length into it. So for all these iterations with the help which were being done with the help of the power n, we replace that n with p for the pumping lemma. So we rewrite the language a to the power p, b to the power p, and c to the power p. Now we need to split s into 5 parts: u, v, x, y, z. So how we can split this value, we'll see in the next slide. For example, p is the pumping length 4, so we need to establish the string first, and then we can split the string into 5 parts. So if we are taking p4, then s, the string, must be a to the power 4, b to the power 4, and c to the power 4. So here is the combination. So case 1, v and y each contain only one type of the symbol. That is the case which we are going to implement in this particular example. So as a were 4, so these are 4 a's, 4 b's, and 4 c's, and we need to split this string into 5 parts where v and y only contains one type. So here v is containing a and y is containing c element. Whatever is in between v and y must be taken as x, whatever is before v we can say u, and whatever is after y we can say z. So if I is equal to 2, so then we are having a new string. So by changing vi as v to the power 2, so we can have 2 a's twice. So in the green color you can see 2 a's comes twice. There are 4 a's, and same for y to the power of I, that is 2. The small c, which is in blue color, comes twice because of the power 2. So here a's are 6, b's are 4, and c's are 5, which cannot be generated with the help of the actual grammar, that is a to the power n, b to the power n, and c to the power n, because all the powers are same. Here we are getting a string which with different powers, so this is a contradiction of the given language. Case 2, either v or y has more than one kind of elements, so we choose v as a combination of a's and b's, so it's a boundary related element. Same for y, we can leave the y for one single element. Even we can have y with in between b and c, so that is not an issue, but here we are simply taking y as c. So again, if we take I is equal to 2 and we give this power to v, so this 3 a's and b comes twice. So 3 a's and b, then 3 a's and b shows the 2 times movement of v, and 2 small c's comes because of the iteration of y to the power 2. So here a's are 7, b's are 5, and c's are 5. This is the contradiction to the given language. Also the sequence has been changed. The a's are in a continuous manner, but whenever b comes, the b should retain its combination. It cannot regenerate a, because the language shows that all the a's should comes first, then b's, and then c's. But in our string, which is pumped, gives different sequence of characters, so it gives us a contradiction. So that is how we can implement pumping lemma in order to prove whether the given language is context free or not. So here is the class practice problem for you guys, and here is the language which is basically w and w belongs to zeros and ones, such that s is equal to 0 to the power n, 1 to the power n, which is 1w, and then again because there are two w's, so 0 to the power n and 1 to the power comes again, so where n is greater than equal to 0. So you guys need to convert this n into p, and then you have to give a pumping length, whatever length you would like to give, and from that particular string you can split the string into 5 elements, and you have to choose v and y accordingly and make different cases which contradicts the condition of any context free language, so that you can easily say or establish the proof that the given language is not context free. So that's all. Thank you very much.